What's the best way to remember electrophilic attack on aromatic compounds? Easy. Just think of electrophilic attack on alkenes. In bromination, bromine approaches the pi cloud, becomes polarized. The electrons feed from the pi cloud to the first bromine, and the second one leaves as bromide, giving a carbocation. You were probably taught that the bromine leans over and forms a bromonium ion, but let's stop right there at that carbocation stage. So the first step is the same for aromatic compounds. And to make a good comparison, let's look at cyclohexene. Cyclohexene adds electrophiles to form a secondary carbocation in the six-membered ring. Benzene adds electrophiles, the electrons feed through again, to form a secondary carbocation in the six-membered ring. The difference is this time it's stabilized by resonance onto the two double bonds. Another difference is we've lost the aromatic energy of the benzene. That's bad, but we'll get it back soon. So in nitration, we add the nitronium ion. It's the nitrogen that becomes connected to the carbon. The electrons feed through onto the oxygen, and we form that tetrahedral intermediate resonance stabilized again. For cyclohexene, remember the electrophile adds secondary carbocation. The next step would be addition of a nucleophile. So we've added the nucleophile and E, whatever that is, across the alkene. For benzene, we add our electrophile. The nucleophilic attack doesn't proceed. To discuss why it doesn't proceed, it's handy, it's useful to you to draw in that hydrogen where the electrophile is added on that same carbon. Don't forget that hydrogen. You need it. You need it because that's the hydrogen that's going to leave as a proton. And the electrons will push back in, regenerating the aromatic ring, getting all that energy back. So we've got not an addition product, but a substitution product. It's as if deprotonation hijacks the addition reaction and takes it to a substitution, because that way the aromatic stabilization is regained. Electrophilic aromatic substitution is not an addition. We've taken away a proton and we've replaced it by E+. Please commit that to memory because it's general, it's useful. All electrophilic aromatic substitution reactions on benzene proceed like this. Step 1, always the same. The electrophile adds carbocation, tetrahedral intermediate. Don't forget to draw in that proton. Delocalize the carbocation if you need to show it's stabilized a bit, but not as much as the aromatic energy of the benzene was giving us in the first place. That first step is usually the slow one. Second step is deprotonation, regenerate the aromatic energy to give a substitution product. So if E plus is Br plus, then E is Br, and we get bromination. If E plus is NO2 plus, so E is NO2, we get nitration. Addition of an acylium ion gives acylation. An addition of SO3 plus joins the carbon and the sulfur to get sulfonation product. If you would like a little bit more detail, then try to remember where you get the reagents from. But I don't think that's as important as the fundamental mechanism. So for bromination, we need Br2 and a Lewis acid, actually, something like ferric bromide, to polarize the bromine a little bit more than is required in an electrophilic attack of bromine on an alkene, which doesn't require Lewis acid. Acylation, the acylium ion comes from an acyl chloride in the presence of a Lewis acid. Aluminum trichloride is a nice one. It will abstract the chlorine, leaving us that acylium ion to do the electrophilic attack. If sulfur trioxide is bubbled through sulfuric acid, the sulfuric acid protonates it, and we get what's called furamine sulfuric acid. SO3 plus is formed in that medium, That's the electrophile for sulfonation. I hope you can draw the structure of nitric acid and get the bonds and charges correct. If we take nitric acid and put it in a stronger acid like sulfuric, an OH group of the nitric acid is protonated, water leaves, and that leaves NO2 plus to do nitration. Thank you very much for listening again. Bye-bye.